we will go through the next class, that is the TP10. In this class we will go through the differential momentum balance or the equation of motion. In today's class we will try to understand what is differential momentum balance, differential momentum balance, or also called as equation of motion. Similar to the previous class, here also, because I am talking about the equation of motion, so the fundamental principle which should be utilized here is the rate of change of momentum, the rate of change of momentum that should be equal to the sum of forces acting in a system. In other words, the Newton's second law of motion, that is the rate of change of momentum is directly proportional to the force applied on the system, and it will work in the same direction, the direction in which the change of momentum is going on. So, taking this fundamental principle of the dynamics, such as the Newton's second law of motion, I am going to derive the differential momentum balance equation for the fluid flow. So, that is the Newton's second law of motion. This is the fundamental principle of physics which is being utilized for the present case. As you know that in order to arrive at this type of fundamental balance equation, it is necessary to have a volume element, or often called as control volume, in the fluid element. Taking the traditional rectangular cuboid, rectangular parallelepiped or cuboid, in this case also I am assuming here a differential element here, taking the axis x, y and z in this manner. This is x axis, y axis, this is the z axis. So, this is our control volume. Here again, this is the point having the coordinate x, y, z, is the meeting point of all the faces through which momentum is entering the control volume, whereas this point having the coordinate x plus delta x, y plus delta y, and z plus delta z, it is called the meeting point of all these faces through which momentum is being released or relieved from this control volume. So, now first the assumption. What should be the assumption? Assumption here is no electric or magnetic field effect, no electric or magnetic field effect is there in the control volume. The basic philosophy behind the assumption of such a thing, that there is no electric or magnetic field, is only due to the fact that you have to consider only the gravity force and the forces exerted due to the matter present in the control volume for the present case. If you consider the electric and magnetic flow, electric and magnetic field effect at the very same time, in that case you have to consider the Earth's magnetic field as well, and you have to consider the magnetic field created by any type of flowing current as obtained through the Biot-Savart, Laplace law and other laws. So, in order to make the discussion in a convenient manner, or making this discussion simple, we are assuming that there is no electric and magnetic fields are there in the control volume. So, let us assume, let rho is the density of fluid, and here rho Vx is the amount of momentum per unit volume along the x direction. Let us assume tau xx, because of the fact that if I am saying that the rate of change of momentum is equal to the sum of the net forces acting over the system. So, if any normal stress is being applied to this control volume under consideration, then some part will be there in the terms of the normal stresses, some part will be there in the form of the shear stresses. So, here I have assumed that the tau xx, tau yy, tau zz, these are called the normal stresses. On the contrary, these quantities such as tau xy, tau xz, tau yx, these are the shear stresses. Now, labeling of all the quantity of the momentum, that is the entering and leaving the system. So, let us suppose considering this x direction, the quantity of the momentum entering is the rho Vx at the value of x, delta y, delta z. And the leaving momentum is rho Vx, the value of this quantity at value x equal to x plus delta x into delta y, delta z. Similarly, if I am taking the positive direction of y, that means in this direction, so this Vx, Vy at y, delta x, delta z. Similarly, the quantity which is leaving, the momentum which is leaving along the y axis through this control volume, that will be equal to rho Vx, Vy at the value y plus delta y into delta x, delta z. Similarly, if I am taking the z direction, that is the direction perpendicular to this xy plane, that is maybe the perpendicular to the blackboard. So, this direction, in this direction we have to assume the quantity which is entering, that will be equal to rho Vx, Vz, the value at z equal to z into delta x, delta y, and similarly the quantity which is momentum which is leaving along the z direction is rho Vx, Vz, the value at z plus delta z into delta x, delta y. Apart from this momentum balance, we have to consider the force balances as well. So, denoting the force balance by some other color, here tau xx is a normal stress acting over the x direction. So, let us suppose this will be tau xx at the value x equal to x. Similarly, leaving this direction, tau xx, that is the normal stress at x equal to x plus delta x. Similarly, along the y axis, along the y axis this direction, that will be equal to tau yx at value y equal to y. Similarly, leaving in this direction in the positive y direction, that is the tau yx into at the value y equal to y plus delta y, because this is your delta x, this is your delta y on the y axis, and this is along the delta z, that is the delta z along the z axis. Similarly, taking the third one, that is along the z axis, that will be the value tau xz at value z equal to z or zx, you can write, for maintaining the tradition, tau zx equal at z equal to z, and similarly leaving the z axis, that is equal to tau zx at the value z equal to z plus delta z. So, this is all about the balance of the momentum as well as balance of the normal stress as well as the balance of the shear stress on the control volume as shown in the figure. Now, momentum balance. Momentum balance over the control volume can be given as rate of momentum input minus rate of momentum output that should be equal to that with respect to the CV, that is control volume, that should be equal to rate of change of momentum over the control volume minus summation of net force on the control volume. Let it be question number 1. Because of the fact that you have to have the ideas about the nature of all these forces, magnitude of all those forces as they are flowing in and they are flowing out through the control volume. So, it is necessary to quantify all the terms in the parenthesis here first, and applying those magnitude in the equation number 1, you will get the differential momentum balance for the present case. So, come to the derivation part. Considering the x direction and unit volume, so the x component of momentum entering the control volume per unit time, that should be equal to how much? That should be equal to rho Vx dx x delta y delta z plus rho Vx Vy at y delta x delta z plus rho Vx Vz at z delta x delta y. Let it be question number 2. X component of momentum x component of momentum leaving the control volume per unit time, that should be equal to how much? You take all the components which are leaving, so that will be equal to rho Vx, the value at x equal to x plus delta x into delta y delta z plus rho Vx Vy, the value at y plus delta y delta x delta z plus rho Vx Vz, the value at z plus delta z delta x delta y. Let it be question number 3. So we have evaluated this quantity, Now let us come to the third one, that is the rate of change of momentum over the control volume. Rate of change of momentum over the control volume, that should be equal to delta by delta t rho Vx into delta x delta y delta z. Let it be question number 4. This is all about the momentum balances over the control volume. So far as the third parenthesis first three parentheses are concerned, this quantity I have evaluated, this quantity has also been evaluated. Now the question for the summation of net forces over the control volume, that is the last thing which is to be determined in this case. I am reviewing this part again in order to have the idea about the summation of net forces. Now, if the electrical and magnetic field, as we have neglected in our assumptions, so first try to emphasize that what are the nature of forces acting over this control volume. So forces on the control volume can be classified in two parts. First is the body force, or it is called bulk forces. These bulk forces are acting over the entire control volume. The second one is the superficial forces. These forces have a characteristic that they will act over a particular plane or they will act over a particular direction. Such type of forces what are called as superficial forces. So far as the body forces, that means those forces which are acting over the entire control volume, these are the two kinds. First is the gravity force. This can be further classified in two parts. First is the gravitational force. Another is the force due to matter inside the control volume. So far as the superficial forces are concerned, this is are of two types again. The normal forces and another is the tangential forces. All these quantities such as tau xx, tau xx, tau yy, tau zz are all these are the normal forces or normal stresses, whereas tau xy, tau yx, tau zx, all these are the tangential forces or shear forces. Now let us try to evaluate each and every pressure force term. Now we will evaluate the every force term one by one. So let us evaluate all the forces acting in a separate manner. Now let us quantify the different forces. First is the gravitational force. Gravitational force in the x direction, that will be equal to Fg, that will be equal to density into component of g along the x direction into the volume delta x, delta y, delta z. Let it be question number 5. Now forces due to the presence of matter, due to the presence of pressure difference, that matter creates a pressure difference, on two faces of an element having normals along x direction. If I am considering the two surfaces which are the normals along the x axis, that means this is the first surface which has the normal along this x axis. Another surface will be this surface has the normal along the x axis. So the forces due to the pressure difference on the two faces having normals along the x axis, that will be equal to pressure at x equal to x into area, that is the force, because you have to calculate the force. So the pressure into area minus P value at x equal to x plus delta x into delta y delta z. Assuming the linear variation of the pressure, this quantity may be evaluated as P x equal to x minus P x equal to x plus variation of P with respect to x into this delta x. The whole quantity needs to be multiplied with delta y delta z. So this will come as minus delta p by delta x, delta x, delta y, delta z. Let it be question number 6. Net force Fxx acting due to the normal component of stress, So if I am assuming the x direction, what should be its normal plane? That is the yz plane. So net forces Fxx acting due to the normal component of the stress on the yz plane on the yz plane, that should be equal to tau xx at the value x equal to x minus, similar to this, minus tau xx at the value x equal to x plus d by tau xx by d by x into delta x whole multiplied by the area of this yz plane, that is the delta y delta z. That should be equal to minus d by tau xx by d by x delta y delta z. Let it be question number 7, where this tau xx is the normal stress per unit area along the x axis, This is the normal force that I have evaluated. Now come to the shear force. Similarly, so the net force acting due to tangential stress component on the xz plane, that means this plane, that is the xz plane, can be given as fyx, that is equal to, similar to previous case, tau yx divided by tau y delta x delta y delta z. That will be question number 8. And similarly fzx, that is equal to minus tau zx by tau z d by z into delta x delta y delta z. 9. Let it be question number 9. So the summation of net force over the control volume, that should be equal to, first is the gravity force, that is equal to Fg plus Fp plus Fxx plus Fyx plus Fzx, that is equal to rho gx minus d by p by d by x minus d by tau xx by d by x minus tau d by y x d by tau yx by d by y minus d by tau zx by d by z into delta x delta y delta z. Let it be question number 10. Now from equations 1, 2, 3, 4, that is the equation which have been written in language, that is for the momentum balance, that is equation number 1. The x component of momentum leaving, that is equation number 2. X component of the momentum, x component of the momentum entering, that is equation number 2, x component of the momentum leaving the control volume, that is equation number 3, and the rate of change of momentum in the control volume, that is the equation number 4, and the summation of the net forces, and equation number 10 we can write better to write this portion now. Now this diagram has lesser utility, so we can write here rho Vx at the value x equal to x minus rho Vx at the value x equal to x plus delta x into delta y delta z plus rho Vx Vy at the value of y equal to y minus rho Vx Vy at the value y plus delta y into delta x delta z plus rho Vx Vz z minus rho Vx Vz at the value z plus delta z into d by x d by y delta x delta y, that should be equal to the rate of change of momentum taking place in the control volume rho Vx delta x delta y delta z minus summation of the net forces rho Gx minus d by p by d by x minus d by tau xx by d by x minus d by tau yx by d by y minus d by tau zx by d by z into delta x delta y delta z. Dividing the whole expression by this quantity, dividing the whole expression by d by x d by y d by z and taking the limits delta x tends to 0, delta y tends to 0, delta z tends to 0, we can write the equations which we can write now. You can write d by d by x of rho Vx Vx rho Vx, keeping this at one side and transposing this to the left hand side or right hand side, that will be transposing this to the left hand side, we can write this quantity that is equal to minus d by d by x rho Vx Vx, okay, plus taking minus in the outside plus d by d by y rho Vx Vy plus d by d by z rho Vx Vz bracket close that is equal to this minus d by tau xx by d by x plus d by tau yx by d by y plus d by tau zx by d by z. Let it be question number 11. Equation number 11 is equation of motion along the x direction in a similar fashion equations for y and z directions can be given as d by d by y rho Vy, that is equal to minus d by d by x rho Vy Vx plus d by d by y rho Vy Vy plus wait for a while. Here in this equation number one term has been left out. That equation, the term here minus rho gx minus d by p by d by x, this also needs to be incorporated, and that will have the plus sign if you transposing on the opposite side this quantity. This equation stands for the equation of motion in the x direction. So plus d by d by z rho Vy Vz plus rho gy minus d by p by d by y minus d by t xy by d by x plus d by t yy by d by y plus d by t zy divided by d by z. Let it be equation number 12, that is the equation along the y axis. This is the y direction equation. Similarly, the equation along the z axis will be given as d by d by z rho Vz, that should be equal to minus d by d by x rho Vz Vx plus d by d by y rho Vz Vy plus d by d by z rho Vz Vz plus rho Gz minus d by p by d by z minus d by tau xz by d by x plus d by t yz by d by y plus d by t zz by d by z. Let it be question number 13, that is along the x axis. Now equation number 11, 12 and 13 are the differential momentum balance equation or equation of motion of fluid flow along the three mutually perpendicular Cartesian axes x, y and z. So equation number 11, 12 and 13 are the equations of motion of fluid along x, y and z axes respectively. Here you can easily emphasize the fact that there is one pressure term, that is the P. There are three velocity terms Vx, Vy and Vz, and there are 9 stress terms, shear stress terms are there. Shear stress and normal stress terms are there. So 1 plus 3 plus 3, 9, total 13 variables are there in the differential momentum balance equation. Till date you have one equation of continuity and the 3 equations of motion. That means you have 4 linear equations, whereas the quantity which to be arrived are the 13 in nature, 13 in magnitude. The question arises, from where other rest 9 equations can be generated. This will be a subject matter of the next class, that how you obtain the 9 rest equation in order to arrive the solution for the differential momentum balance equation. So in the next class we will teach you that how those 9 rest equation can be arrived to have a solution of this momentum balance equation. Thank you.